So question 5 essentially tells you to find a t-value for when 20% of the krill from 1976 is present. So the first step is to realize that 20% means that d of t is equal to 0.2 of 1976. So now we can try and solve for d of t. Because the question as well also says that t is measured in years since 1976. So you can essentially figure out that when t equals 0, that will be when 1976 occurs. So if you let t equal 0, you can solve for d of 1976. So that's what I did. And you obviously get 100 krill per meter squared, which makes sense because it's also your initial amount here. Now, once we can figure that out, we can then figure out how much krill we're looking for. Because d of t, if it's 20% of 1976's krill, d of t is equal to 0.2 times 100, because d of 1976 is 100. And then we can figure out that d of t is 20 krill per meter squared. And now that we figured that out, we can essentially start answering these questions in the box. So the initial value for the exponential model, as shown through this calculation, is 100. The decay constant, we can read that from the model, is negative 0.03. And the value that you're trying to find is the t value that corresponds to 20 krill per meter squared, and that's because of this. And your initial guess is 30 years. So that satisfies this section. But the second part of it is to write the output of what the code will produce. So to do that, you have to go back up and look at the code. And in the code, it actually tells you the derivative of the decay function, and it tells you the decay function. Since the decay function is exponential, the derivative is essentially whatever the k value is in front of the t goes down here and multiplies with the a. So you get that. And this is t, but in this case, we've subbed in 30. The reason we've subbed in 30 is because we are now evaluating these two functions here. So exponential decay function is this section here. And when you plug in d of 30, you get a value of 41. And then the second one is the gradient function, or the rate of change function, or the derivative. And when you plug in 30, you get negative 1.22. So therefore, we can figure out that we now have all the information we need for Newton's method, because we know that t naught is 30, and we also have the normal function and the derivative. Now, I'll change this when I submit the exam. These variables should be t1, 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 and this one should be t naught. I'll do that after I've finished recording this video, but for the time being, let's just say this is t1 and this is t naught. So because this is t naught, we can sub 30 into here, and we can go 30 minus this value goes there, this value goes there, and then we can figure out that the first iteration will produce a t value of 63.61. If you increase the steps, this value will become more and more accurate, but yeah, that's the output that we would expect from just the first iteration.